Pretty straight. Moving on, number 7. What must be the acceleration? So A equals, we don't know, of a train in order for it to stop. Vf equals 0. From 12 meters per second. Vi equals 12 meters per second. In a distance of delta x equals 541 meters. And then we assume it's accelerating uniformly. Okay, we are looking for an acceleration in terms of final velocity, initial velocity, delta x. What's missing there? We don't know the time. Which one of these formulas gets me using those without the time? You guessed her, right there. So we can start with Vf squared equals V initial squared plus 2 times the acceleration times the change in position. And if you want to plug in and solve, that's great. I prefer to rearrange, and you get A equals Vf squared minus Vi squared over 2 times acceleration times, 2 times the change in position, because we put the acceleration up there, my bad. And then you plug and chug. So really what you guys are wrestling with, my guess, the biggest troubles we're having is listing the material, spotting the correct formula, and then possibly rearranging. This is just algebra. I can't spend a lot of time teaching you guys algebra, but I do want to help you get good at it. So you can know that there's a reason you learned that, so we can use it. Moving forward, number 8. All right, a car will skid to a halt. Vf equals 0. That's what a halt means. With a uniform acceleration of negative 9.4 meters per second squared. If you measure skid marks that are 34 meters long, that tells us the distance it was decelerating or accelerating negatively or slowing down is 34 meters. What speed was the car going just before? So we're trying to find V initial. All right, here we go. We've got Vf, we've got acceleration, we've got delta x. What don't we have? We don't have time, so we're back to this guy again. It's a good equation. So end up with Vf squared equals Vi squared plus 2 acceleration delta x. You can plug your data in and you can hit the solve function, or you know me, I like to rearrange, so you end up with V initial equals the square root of 2a delta x minus Vf squared. If you're not sure how I got from this equation to this equation, see me and let me help you with your algebra. I'll be your algebra. All right, moving to number 9. All right, an airplane touches down at a speed of, that sounds like an initial velocity, equals 55 meters per second. On a runway that is 600 meters long, we ideally have a 600 meter runway. The plane can decelerate at a uniform rate of 2.5 meters per second squared. So if it's decelerating and it started with a positive velocity, is this acceleration positive or negative? That's right, it's negative 2.5 meters per second squared. And we know that the final velocity that we're shooting for will be 0 because we want it to stop. So what are we actually trying to find here? Will the plane be able to stop before the end of the runway? What are we solving here? Well, I guess what we need to know is, with this information, will it stop in enough space or distance or dx where it's not longer than 600 meters? If we solve for delta x and find that the distance is something like 700 meters, that means it needs 700 meters to stop, which means 600 meters is not long enough and the plane will crash. Yikes, this is important stuff. So let's figure it out. Well, Vi, delta x, A, Vf, we know these things. I'm sorry, we don't know delta x. We're solving for delta x to see what the real stopping length is in terms of A, Vf, and Vi. Here we are again. So we start with Vf squared equals Vi squared plus 2 acceleration times delta x. That's the equation that doesn't involve t. We're solving for delta x, so we rearrange. Delta x equals Vf squared minus Vi squared minus 2a. There's your final equation. I think you guys, hopefully you'll be just as satisfied as I am when you work the units out and find out that it provides the perfect units for an answer. All right, moving forward. You guys are doing great. We have another 4 problems to do. If you're still with me, that's awesome. All right, number 10. A cyclist is riding along at a constant velocity of 15 meters per second. V initial equals 15 meters per second. You can hear my dog barking in the background. He then accelerates at a uniform rate. A equals 0.50 meters per second squared over a distance, delta x, of 64 meters. How long did he accelerate? How long did he accelerate? How long? Is that delta x? I've got delta x. What do they mean by how long? If I ask, how long did you work on this problem? What units are we talking about? You're talking about seconds or minutes. How long did he accelerate is asking about time. We're solving for time. So this one's tough. There's a couple ways you can do this. One, you're looking for time in terms of v naught, acceleration, and delta x. And if you do that, you can find out that it's this guy, but this provides a couple problems. Let's just check it out real quick. X equals v naught t plus 1/2 at squared. If you like, you can use this. The problem is you end up with a quadratic situation. If you are comfortable with quadratics, knock yourself out. Go for it. You'll get 2 answers. One will be negative, one will be positive. You need to choose which of those times make sense. Can you have a negative time? I don't think so. So you choose the positive one. Or what you can do is the first thing you can do is you can find your final velocity by using this. Vf squared equals v initial squared plus 2a delta x, because we have that information. And you can get your final velocity this way. Then you can plug that in and you can use Vf with this. Vf equals V initial plus AT, and then rearrange, so you end up with T equals Vf minus Vi over A. You guys, this is a 2-step problem if you're not comfortable with quadratics. It's hard, it's complex. If you struggled with it, that means you're a normal teenager. But I do want you getting comfortable with seeing how far you can get just taking stabs at it. Lining things up and looking for an equation is the key to success in physics and in life. Moving forward. Here's the other hardest one. By the way, number 10, the one we just did, was probably the hardest one on the sheet. Let's do another one that's similarly difficult. All right, almost there, you guys. You're doing great. The driver hits the brakes. His car decelerates at a uniform rate of 2.0 meters per second. So we have an acceleration. If it's decelerating, is that positive or negative? It's negative 2.0 meters per second squared. That should say squared there. Sorry, guys. His car stops in 9 meters. So delta x equals 9.0 meters. How long does it take him to stop? If it says, how long did you do something? We're looking for time again. All right, and we also know the final velocity is 0 because he's stopping. So using Vf, delta x, and A, we might be tempted to use this. Delta x equals V initial t plus, minus, my bad, final t minus 1/2 at squared. That's this bottom one here. We know Vf, we know delta x, we don't know t. We know the acceleration, so plug it in here. Yikes, this looks like a quadratic situation. Oh my goodness, what do we do? Wait 1 minute. Vf is 0, so that term goes away. So really what you have is delta x equals negative 1/2 at squared. Think about it. Final velocity is 0, so final velocity is 0. This part goes away. You just end up with negative 1/2 at squared. And you end up, if you rearrange it, t equals delta, or the square root of minus 2 delta x over a. This might freak you out. Wait a minute, you can't take the square root of a negative. But remember, what kind of acceleration did we have? We had a negative acceleration. That negative sign and this negative sign will cancel out. You'll end up with a positive that you can solve for. Trust the math. Trust the algebra. 2 more. A train can speed up at a uniform rate of 15 meters per second squared. So acceleration equals 15 meters per second squared. In what minimum distance delta x equals, we don't know. Attain a speed of, so Vf is the speed it's trying to get to, so that's 25 meters per second if it starts from rest. V at 0 or V initial equals 0. Here we go. Acceleration, Vf, V naught, no t. Where are we going? Right there again. So you end up with Vf squared equals Vi squared plus 2a delta x. We rearrange, delta x equals Vf squared minus Vi squared over 2a. Plug and chug, you're in business. Line up what you know, what's missing, find the equation, you're in business. Last problem, guys, doing awesome. If you're still actually with me 20 minutes into this, holy moly. Drag racer can reach a speed, that sounds like a final velocity, if it can reach that speed, 53 meters per second, over a distance, delta x, of 120 meters. Over what distance can it reach a speed of 85 meters per second? Now you might be wondering why I write this different. Because there's two situations. They say it can reach this speed if you have that much distance. So if you have a new distance, it can reach that speed. So two situations here. I'm going to call this situation 1, situation 2. Situation 1, what are we trying to find? Let me think. I've got a final velocity. Oh, I have an initial velocity because drag racers start from 0. So what I can find here is the acceleration. I can go Vf squared equals Vi squared plus 2 acceleration delta x. Find my acceleration is Vf squared minus Vi squared over 2 delta x. Once I do that, I'll have the acceleration for the cart, and then I can throw it over there. And once I now know the initial velocity of 0, because remember, we're talking about a different car, same acceleration as the first, but just going to a higher speed, what distance? So now you know the initial velocity, the acceleration, the final velocity, and you can, once again, Vf squared equals V initial squared plus 2a delta x. We know that because there's no t, so we use the one with no t. Rearrange, delta x equals Vf squared, that's Vi squared over 2a. Plug and chug, you should end up with the proper answers. Okay, this has been a long time, it's 20 minutes, and that was me going super fast. I hope you did all right with this. If you need help, let me know. See ya.